C'est un très grand plaisir d'accueillir Ralph WILLOX. Il vient de l'université. Alors moi, je ne sais pas, je dis Komaba, mais peut-être que Tokyo, c'est le plus approprié.
C'est l'université de Tokyo à Komaba.
L'université de Tokyo à Komaba. Et qui va donc nous parler du problème de détecter l'intégrabilité dans les systèmes discrets. Thank you.
Thank you very much for the invitation to speak here. I think I gave a seminar at the same place around 91 or 92, very long time ago. It's a pleasure to be here again and to be able to give this seminar. So yes, the title is a bit long. It was pointed out to me that it was too long, so I'm going to get used to this. Try to tell you a little bit about how integrability for discrete systems is defined nowadays, and why the definition might be to you. Of course, it might not be exactly what physicists have in mind when they talk about integrability for certain systems, and why we might need to refine the current definition a little bit, and the work. Okay. I will have to touch this from time to time. This goes away or not?
C'est un clic, ça devrait être bon.
That's okay. Okay. So the talk is at least in part based on these two references. There will be some more references at the end. These are very recent references, but there will be some older work, especially in the beginning. Yes, so I think it's best to explain what I mean by integrability and the problem of detecting integrability on an easy example. It's actually a very nice example because it encompasses all different types of integrability and non-integrability that I want to tell you about. So it's just basically a three-point map on P1 cross P1, so on the projective, or on P2 on the projective plane if you want. And there is a free parameter, which is a non-negative integer, this exponent, and depending on the value of the exponent, you have all sorts of different behavior for this very simple recursion relation, nonlinear recursion relation. So this is the typical behavior. It's out of the way. When k is 0, everything is completely trivial. I say it's completely trivial, but actually I have to comment on this afterwards because it's not the nice type of triviality that you want to take into account when discussing integral systems. So when k is 0, you just have a periodic mapping with period 4. So this is the typical orbit. If u and v are two initial conditions for x0, x1, then these are the iterates, so it's just period 4. When k is 1, the mapping has a rational invariant, so actually just the direct product of two quadratic curves. So this is something you would want to call an integrable system. It has one conserved quantity. It has, well, it's an order 2 equation if you think of it as an equation, so you can actually integrate. And you know how to use this invariant to actually write down solutions for the initial value problem for the map. When k is 2, you are in a similar but slightly more complicated situation where you have an elliptic invariant. This defines an elliptic curve. So the curve itself is completely invariant. If you give the initial conditions, the curve is completely defined, and the map is an example of a very famous type. It's people in the field call it QRT maps. And basically what the map does, it defines a translation on this elliptic. So that's also a case that you would want to call integrable. And then actually you can prove that when k is at least 3, that there are no invariants. So as a physicist, you would want to call this a non-integrable situation.
Yeah, sorry. Yes. Why do you take this particular mapping? Why not something like 1 over xn minus a constant, for example?
Because this one has all the different behaviors that I want to discuss afterwards. It's not. I could have taken any other map, but for this map, actually, there are some nice things that I want to tell you. Yes, if you bear with me for at least 10 minutes, then you will see why this map is nice. It has certain nice features for pedagogical reasons. I mean, I could have taken any other. Well, any other map, you have to work a little bit to have one that has all the behaviors. And you need at least one free parameter. But yes, I could have taken any other example. I mean, this example is not special at all. So, as I said, if you think of integrability as defined in terms of having sufficiently many invariants to actually integrate the map, then these two cases would be integrable. As I said, the first one, the periodic case, is also integrable. You define integrability through the existence of an integral. If you know the orbit, you can always construct an integral. Now, the annoying thing with periodic maps is that you do not control the period. So if the period of the map is 4 or 5, then yes, I mean, you can assess by just iterating that it's periodic. The period is 2 billion. There is no good way without doing some more fancy mathematics. For this type of map, you can actually ascertain the periodicity quite easily, but for higher order maps, it might be very difficult to assess that it's periodic. So that's the problem with periodic maps. That's why I don't want to discuss anything about periodic maps after this. So depending on your point of view, you could say that there's an invariant, but to construct the invariant, you basically have to construct the complete orbit. There's nothing to be gained from the invariant in this case. And so, as I said, the other cases, they don't have any integrals, so I want to call them non-integral by definition. But the problem is, how do you know that there are no other invariants? Because proving there's an invariant is moderately easy. Proving that there are no invariants is most of the time it's a hard. So how do you? I will want to come back to this point. How do you know that there are no other invariants when k is at least 3? Well, for that, there's a deep connection between the properties for these different cases that I showed on the previous slide and the degree growth of iterates of this equation. I'm calling it a mapping. I'll write it down as a mapping on the next slide. So I'm going to count the degree growth in a rather special way. So I'm not going to count the degree growth of iterates of the map in terms of the 2 initial conditions. It's a second order map, but just in terms of one of the initial conditions. So the first x0 initial condition would be just some generic symbol, no special properties, which I'm not going to take into account when I calculate the degrees. And I'm going to count degrees of iterates of the map for these initial conditions as rational functions of this x1 initial condition. So all these xn's, all the iterates will be rational functions of z, and I'm going to count degrees in terms of z. That's going to be the end. Now, there are some easy ways to actually write down recursion relations for these degrees. When k is odd, you have this recursion relation. When k is even, you have a slightly different one. And so for these initial conditions, which from here, you can actually solve this. So when k is at least 3, an odd integer at least 3, the degree growth is basically maximum. It's just the degree of nonlinearity to the nth power. Asymptotically, that is how the degrees grow. When k is 1, you're in a special case where you can actually explicitly solve this easily, and you find that it's basically, well, it's difficult to see, it's the floor, so it's the integer just less than half of n plus 1. And so this is linear growth when k is 1. When k is 2, you have quadratic growth. And when k is an even integer, at least 4, you have, again, exponential growth, which is slightly slower than the odd case. It's also important to explain why it becomes slow. So these two cases, the cases k equal 1 and k equal 2, were the cases with integrals of motion. And there's an important notion, which is the notion of algebraic entropy, which is defined in this way in terms of these degrees of the successive iterates. And it's basically a qualitative way of measuring the degree growth. When the algebraic entropy is 0, it means that the degree growth is sub-exponential. And more precisely in this case, either linear or quadratic. And those are exactly the two cases where there were integrals of motion. And when the algebraic entropy is greater than 0, it means that the growth was exponential, the degree growth was exponential, and these were the two possible values for the algebraic entropy, depending on k being odd or even. Now, as I said, I'm going to think, I already called it on the slide, I called the equation actually a mapping. You can easily rewrite this equation as a map on P1 cross P1. And now, why does the degree growth become non-maximal? For example, when you were, in the case of exponential growth, but for even values of this nonlinearity k, you had slightly slower growth. Well, the reason is, of course, that there are indefinite points for the map. So an indefinite point, I'm a map in 2 dimensions. It means that basically there's a cancellation between the numerator and the denominator of some of the iterates, which means that I go down to a 4-dimensional 2 variety in the plane. But of course, I'm in 2 dimensions, so that's a point. How do I get to a point? Well, because I pass through singularity first. So the map has indefinite points, and you can reach them only by being sort of lucky or unlucky, depending on your point of view. You choose initial conditions, basically on a codimension 1 variety, and that curve basically collapses to a point that eventually ends up at an indefinite point. That's how the degree growth becomes non-maximal. So, I'm sorry, this was too fast. So this is the unique singular locus for this map. So it's basically the y is 0 and x takes any generic value, non-zero in this case. And if you calculate the first iterate, I write down the multiplicities because they're important afterwards, the multiplicities of the infinity, which come from here. So you basically, but this, on P1 cross P1, this is just the point 0, infinity. That's the first iterate. So this curve collapses to this point. This point is still, the map is still well defined at that point, so it goes to that point, but that point is an indefinite point for the map. And that is where the degree starts dropping, especially by quite a lot in the k equal even case. Now, the map has a very special feature, and that is, coming back to your question, that is the reason why I chose this one. And that is for the following reason. That is that there's something special about the map, that is that the third iterate of this map is special. So the third iterate of this map, if you take the image of the singular locus, you see that it's again a codimension 1 variety. So that is what makes this map a little bit special. There's this notion of singularity confinement, which means that although the singular locus is a singular locus for the map itself, it is not a singular locus for the third iterate of the map, because of the cancellations that happen around this point. So this notion where you can actually jump over the singularity, if you want, by using an iterate of the map, in a sense you enter a singularity through this singular locus, but the length of the singularity is finite, and actually you recover all the information on the initial conditions from the third iteration of the map. This notion is called singularity confinement. And so this map has singularity confinement. There's an important thing. When, not in general, but when k is even. Yes, I should have put that on this slide. So not in general, but for even k, the map has this problem. That's why I couldn't take just any other. I wanted this problem. So when k is even, so I'm writing it as 2m, there is singularity confinement with this pattern. Now, why do I want to present you with a sort of pedestrian calculation? Well, for 2 reasons. First of all, calculating iterates of maps as such can be computationally very, very inefficient. There's actually a much easier way, a much more computationally efficient way to ascertain whether there's this notion of singularity confinement or not. Just iterating the map with a slight perturbation of the initial condition. So the initial singular locus would have a 0 here as initial condition, but I'm not going to say it's 0. I'm going to be close to 0, but not quite to 0. And then I carry through all the iterations up to the third iterate, where I expect to have singularity confinement for the even case. And all these expressions are just rational expressions in terms of the remaining initial condition, this u, and this small parameter epsilon. So if you see that after 3 iterates, you regain at leading order the initial condition here, you lost through the singularity, with some small perturbation in epsilon, you know by some continuity argument that if epsilon was 0, that the third iterate would still be well defined and would depend on the initial condition, so that you're again at the codimension 1 variety. So this is the pedestrian way of ascertaining the fact that you have singularity confinement. Now this will be important afterwards because I want to do this in a slightly more general setting. So the pattern that I wrote down here comes from setting epsilon to 0. Now, there is something special. I don't want to spend a lot of time on this because it's going to be, this is slightly a different story, but there's a small game that you can play with the singularity pattern. So this was the pattern that I showed you on the previous slide. So 0, infinity with some 2m multiplicity, and then again 0. And I want to write down a characteristic polynomial based on this pattern. So the game is as follows. When you see a 0, you write a power of lambda with a positive coefficient, and besides the sign, the numerical value of the coefficient will be the multiplicity. So these zeros have multiplicity 1. So I have 1 times lambda squared, and I have 2 positions later. So I'm decreasing the exponential of lambda, so I have lambda to the 0 with a coefficient 1. And if I have an infinity, I'll put down a negative coefficient with the correct multiplicity. So this, I'm re-encoding this pattern into this characteristic polynomial, and the largest root of the polynomial is exactly the value that gives me the algebraic entropy. So this actually, the exponential of the algebraic entropy is called the dynamical degree of the map. And so the largest root of this characteristic polynomial that I've constructed by this little re-identification of the pattern gives me exactly the dynamical degree of the map. Now, this is not, it looks like magic, but it's not. There's actually a theorem that you can prove under certain conditions. If you have singularity confinement, then you can prove that there is a deep link between the value of the dynamical degree or the algebraic entropy for the map and the patterns that you have. I mean, this map is again very special in the sense that it has only one singularity pattern. So the link is immediate. You could have maps with many singularities, with many singularity patterns, and then the link is a bit harder to establish, but it can still be done. Unfortunately, there are maps where all these patterns are very short, and then there is no way to actually reduce the dynamical degree from those patterns. So there are things to be explained, and those are explained. It's a bit small, but in this paper with some co-workers of mine already 6 years ago. So there are some theorems proving that this is not an accident. This actually works. So this is actually an exact result. Give me a map with just one singularity pattern, I can tell you immediately what the degree growth is just by looking at the singularity structure. Now, there is, why? Well, I have 2 minutes. Why is this happening? Well, actually, the algebra geometric reason is quite deep. But if you just think in terms of complex analysis, then you can sort of see where the link comes from. So as I said, I was calculating degree growth in a rather special way, not in terms of both initial conditions, but just in terms of one initial condition. So that means that all these iterates of the map, in terms of that initial condition, they're just rational functions of one variable, this variable z. Now, you can define, of course, for these rational functions, you can define the degree of the rational function by saying that it's actually the number of free images for any value of the rational function in V1. So choose any omega with multiplicities. If I count the number of free images of this value omega through this rational function xn, that is exactly equal to the degree of the rational function, if I count with multiplicities. So what does that do? Well, it means that if I'm looking at, for example, the number of free images of the nth iterate of the map of the value 0, these free images, they can appear in 2 ways. Either they can be just what they are because of the choice of initial conditions, or since 0, if you enter a 0 in the singularity pattern, you know that 2 steps afterwards you will have another 0 appearing. So that's the second way you can have a 0 appearing for the iterate. So actually, if I should have defined this the other way around, if the number of zeros as what I mean, the number of pre-images of 0 that appear not through a pattern like this, if I call that large or capital Zn, then I know that the number of pre-images of 0, the nth iterate, is actually encoded in this way. It's Zn plus the number of times that this happened 2 steps before because of the singularity pattern. So that's one relation. Now this number is really the degree of the rational function. That should also be equal to the number of pre-images of infinity. Yes, these 2 degrees should match. Now, how do you get infinities? Well, again, if you hit a singularity in this pattern, then you know that the step after that you will have 2m infinities appearing, counting with multiplicities. So the number of times that that happens is Zn minus 1 times 2m. But infinities can also appear periodically with period 2. Because these are not singularities, but the map is such that it basically flips 2 curves. So y equal infinity goes to x equal infinity, back to y equal infinity. So with period 2, you have an infinity appearing as well. Now the claim is for trivial reasons is that these 2 degrees have to match. We have a recursion relation, which is this recursion relation, and the characteristic relation, or the characteristic equation for this linear recursion relation, inhomogeneous of course, is exactly the one that I showed you, which is connected to the singularity pattern. If there's only one pattern, this is basically an explanation why the trick that I showed you works. If you have many patterns, this type of proof is not possible, and you need to do some algebraic geometry. But there's still this link between dynamical degrees or algebraic entropies and the patterns that you find. So this is just in a nutshell why there is this link. Now, what is known about maps of projective plane in general? Well, first of all, singularity confinement, as I defined it on the second slide or the third slide, is actually equivalent to this statement that you can actually regularize the map on some rational surface by a finite number of blowups. Only blowups. The surface might not be minimal, but only blowups suffice, and that's one of the results contained in the famous Dillard-Favre paper from 2001. And then, based on the degree growth, you basically have 4, depending on how you count, 5 types of maps. So if the degree growth is not exponential, there are only 3 possibilities. Either it is bounded, for example, for period maps, the degree growth is bounded. The degree growth is either linear, if it's not bounded, or quadratic. So the 3 cases that I showed you for the example where you had a periodic case, a linear degree growth case, a quadratic degree growth case, that exactly covers these 3 possibilities. If the degree growth is exponential, so then the dynamical degree, so the algebraic entropy is greater than 0, so it's exponential, the dynamical degree is greater than 1, then, so the degree growth is exponential, and then there are some strong results which tell you that the maps are non-integral. So in the first 3 cases, if the map has bounded degree growth, then the map is either periodic or can be shown to be basically conjugate to a projective map on P2. If it has linear degree growth, then you know that there is maybe not a rational invariant, but there is an invariant rational fibration. But the map will never have singularity confinement. If the map has quadratic growth, then the map always has singularity confinement, and there is always an invariant elliptic fibration. Maybe not an elliptic invariant, but an elliptic fibration. Now, the statement is even stronger in the exponential case, because there you can show that there are no invariant fibrations, but the map can have singularity confinement or not. I'm going to skip the numerology because I won't have time otherwise.
What do you mean by having a rational fibration but no rational invariant, or same thing with elliptic?
Well, that's a very good question. The thing is, the fibration, if the action on the fibers induced by the map is just a permutation of the fibers, then you take the product of all of them, you have an invariant. But there is no guarantee that the map induces a finite order action on the fibers. So for the rational fibration case, for the linear growth, that's easy. I can I can cook up an example immediately. And so basically you would have a non-autonomous invariant. So you basically would have an invariant that has non-autonomous coefficients, like exponential functions appearing. For the elliptic case, we don't know the answer. There are some papers claiming that you can only have a finite order action on the fiber, so basically only permutation of the fibers induced by rational maps, but there is no proof of that statement. So there might be infinite order actions after all. In that case, there won't be an algebraic invariant. That's what I mean. There's one interesting thing to do with symmetries for the case where you have exponential growth. There's also a very nice result by Quentin showing that there are no non-trivial symmetries. So for maps, symmetries are basically maps that commute with the original map. And there's a very nice theorem showing that if your map has exponential growth, then it has no preserved vibrations and no non-trivial symmetry. So as soon as you find another birational map that commutes with the original map, then it is related to the original map by one of these relations. So that's also a very strong statement. So in that sense, these cases you really want to call non-integrable, and these cases you really want to call integrable. Here you have it. Maybe not invariant, but at least some invariant structure, which might not be algebraic. In the case of, as I explained, if you have an infinite induced action on the fibers, an infinite order action on the fibers, then you might have transcendental invariants. There are some cases for the linear growth that are known, but in this case, you definitely have nothing that would warrant calling the map integral. So in the two-dimensional setting, everything is really nice. As you calculate the degree growth, and you basically know whether the map is integrable in the sense, in a more physical sense, whether you have any hope of having non-trivial symmetries, or whether there's any hope of actually integrating the map through the use of some invariants. So in the two-dimensional case, everything is clear. Yes. So as I said, well, I can skip this. In the non-autonomous case, because all the map, I forgot to mention this explicitly. On the previous slide, everything was autonomous. As I said, some of the invariants might be non-autonomous if you really want to write them down as invariants. But there are similar statements for non-autonomous maps. If people have questions about this, I can come back to this later. I'm not going to spend time on this now. So I'm going to present. I will talk a little bit about non-autonomous maps because I want to present a different method to calculate degree growth explicitly, based on the idea that you can construct a non-autonomous version of the original map that contains the original map as a special case, and the act of de-autonomizing the map actually tells you everything you want to know about the degree growth. Again, this sounds sort of magical, but again, there's a theorem which I flashed by you on the previous slide, but it'll come back in a number of slides. So as I said, this map is special because for the even degree case, it has this special property of singularity confinement, and there were there was one special case where you had an integrable case with an elliptic invariant, and then all the other cases were non-integrable, so exponential degree growth. And the elliptic invariant case, as I said, had quadratic degree growth, and it had singularity confinement with this pattern. So I showed you one way to use the pattern and deduce a dynamical degree. I'm going to show you another way now to do the same thing, but in an even stranger way. So singularity confinement, as I said, the pedestrian way of ascertaining this property is by basically doing this perturbative calculation. And now the question is, if I change the map and I'm allowing this was a 1, but if I now say I have a free function of the independent variable n. Now, are there choices of functions a, n such that this map still has this property of singularity confinement with the same pattern as the case where I simply had a 1? So you know what to do. You do exactly the same pedestrian calculation, and then you see that the third iterate will still have a singular term. If epsilon goes to 0, this blows up, and you want to kill this term. If this is gone, then you find yourself in the original situation for the autonomous map, where you immediately see that the third iterate basically has no significance. So this imposes this two periodic constraint on this function. So the statement is, yes, you can have a non-autonomous version of the original map, but it's sort of boring because the coefficient function that you're allowed to impose here is just a period 2 function. If this function is period 2, then everything is the same as in the autonomous case. So this map can be extended slightly by adding this lower degree term, a subdominant term. You could of course put all sorts of terms, but I know the answer, so I just put one term. So the minimal choice, or the optimal choice, is this extension. And so an is now a period 2 function, and I ask the same question. This map, are there functions, coefficient functions Bn, that are such that this map now with an being 2 periodic will have again the singularity confinement property with exactly the same pattern as in the original autonomous case. You do exactly the same calculation, you find that the third iterate will have a singular bit, but you see how to kill off a singular bit. So if the B's satisfy this recursion relation, then your map has singularity confinement again with the same pattern. Now, if you look at this recursion relation, you've seen it before. It's exactly the one that defines the dynamical degree for the map. Now, this again looks magical, but again, there are deep geometric reasons why this needs to be the case. So the statement is, if you have this deautonomized, this non-autonomous version of the original map, then actually the asymptotic behavior of the coefficient of this term is actually dictated by the degree growth of the map. It's not a priori clear why the asymptotic behavior of the coefficients should be linked to the asymptotic behavior of your general solution of the map, but these two are intimately linked. So that is the statement. And that is true for all deautonomizations. So the degree growth has to obey that link for all the optimizations, so also the original one. And so actually by deautonomizing your original map, you have a quick way to calculate the dynamical degree and the algebraic entropy for the original autonomous. And that's what we call this method of deautonomization, or the obtaining the dynamical degree of a map by deautonomizing using singularity. That's in this recent paper with some collaborators. Maybe it's best to show both of them. I'm not going to spend time on the details of the proof, but the setting is actually quite general. The only thing you need of your map, of course, you could argue that maps with singularity confinement are very special, but there are many examples of maps that have singularity confinement. And besides linearizable maps, if you're interested for maps of the plane, you're interested in maps that have elliptic invariance, then all of them have singularity, for example. And among non-integrable maps, there are plenty of maps that have singularity confinement. And if you want to be sure that you can use this method to calculate that dynamical degree rigorously, then besides singularity confinement, the only other constraint is that the map has to basically be measure preserving. So not even strictly measure preserving. You need to have a rational 2 form that is actually preserved up to a constant. There are a lot of maps that are measure preserving up to a sign, where the measure simply for sign. The setting is even more relaxed than that. It could be up to a multiple, which could be any complex number, basically. So under these very loose conditions, you can actually prove that there are sufficiently general extensions of your map that do not change the singularity patterns, but where you are sure that one of the coefficients in the autonomous version of your map will pick up the asymptotic behavior of the map itself. And that is a strong theorem. Okay, I'm going to skip this. As I said, the main condition is that you have singularity confinement for your map. Now, why do I say that is the main condition? Well, it is the only way that we found to actually prove the theorem. But there are examples of maps that do not have this property where the method still works. And one example is this rather nice example here. You have this, again, a second order recursion relation with a confined pattern. So these are two patterns. You either have singularity at 1 or at -1, and these have, here you have singularity confinement. And then you have this kind of strange pattern where, I mean, in a sense, if the map is singular, if the forward map is singular, then the backward map has to be singular as well. So this is a rather bad type of singularity. You can actually show that this type of map cannot be lifted to some kind of automorphism of a rational surface. So this is a very bad singularity. Nonetheless, so the degree growth is basically the golden ratio. You already see Fibonacci numbers here in the multiplicities in the pattern. It's not a surprise that it's the golden ratio, but that's the degree growth. It's exponential, but you can de-autonomize the map in exactly the same way as I showed you before. This map has exactly the same singularity confinement property as the original one, under the condition that the coefficient function satisfies this recursion relation, the largest root of which is exactly the golden ratio. So this is probably not a fluke, but we have no idea how to prove that this will be true in general. So the singularity confinement condition is crucial to the proof that we came up with, but it seems that there are maps that have similar properties without singularity, or only partial singularity. They could have very bad singularities besides those, but we don't know why this happens, and we don't know how. So there's something to be done there. So what is known for higher order recursion relations, or for higher dimensional maps? Well, there is a general notion of regularization that also allows you to calculate dynamical degrees in principle. But the problem with doing blow-ups in higher dimensions is that for mappings of the plane, if you do blow-ups, then you don't create any new singularities by doing that. That is no longer true in higher dimensions. So it's when you start doing the blow-ups, it's completely unpredictable what will happen. You have to work very, very hard. So it might not be a very efficient way to actually. I was sorry. Is this button? Yes. There were a lot of conjectures about the dynamical degree for higher order maps being algebraic integers, but that has been disproven in a recent paper by this is Jeremy Diller and his group. There are counterexamples already in 3 dimensions where the exponential of the algebraic entropy is not an algebraic integer. There are conjectures about the sub-exponential part of the degree growth. There's a famous conjecture by Silverman claiming that apart from the exponential growth, the maximal growth can be like that, but that has not been shown in general. It's been shown for quite general classes of maps, but not in general for birational maps. There's also a notion of using different types of entropies to basically qualify integrability. One would be a method that relies on the arithmetic height. You could choose any height function basically. So one popular height function is just you start from rational initial conditions, so really numerical initial conditions, and you look at the growth rate of the, well, actually the number of digits in the denominator or numerator of the iterants. That would be one arithmetic height function that you can use, and there is a conjecture that in many cases the dynamical degree, the first dynamical degree, will coincide with this arithmetic degree. Now, and that is basically a very popular and numerically very efficient way to calculate or to estimate degree growth and dynamical degrees or algebraic entropies, which was already introduced by Halbert 20 years ago, which is called the Diophantine method. But the problem is that there are no real rigorous proofs. The dynamical degree has been shown to exist for maps in arbitrary dimensions. There is no general existence proof for the arithmetic degree. Again, for large classes of maps, it has been shown to exist, but not in general for birational maps on PL. That's one problem. And it's been shown by already 8 or 9 years ago by Kawaguchi and Silverman that if it exists, it cannot exceed the dynamical degree. But equality has only been shown in special cases. And there are some very interesting sufficient conditions given by Matsuzawa and co-workers, but there's no general proof that these two degrees have to coincide. So it can't be bigger, but there's no clear statement as to when it will be the same. Okay, so I have 5 minutes left. So I will give some examples of things that happen in the case of higher dimensional mappings, things that are nice, and then things that are puzzling. So one case is this map, which can be of any order. Yes, so n measures the order, so it's an n+1 order map. M is again just a parameter regulating the degree growth, and it's very nice because it has only one singularity, and it has singularity confinement with basically a length dictated by the order of the equation. So here, all these dots are n-2 regular values, so nothing special, no zeros, no infinities. And you can play the same game. You can sort of extend this map with subdominant terms that don't muck up the singularity pattern. And you can allow for free functions as coefficients. And then you look under what conditions this non-autonomous extension of the original map has singularity confinement with exactly the same singularities. And you see that there are two conditions. Basically, the dn's are defined in terms of the cn's. The cn's satisfy this horrible looking recursion relation, and the largest root of the corresponding characteristic equation coincides with the value of the arithmetic degree that you find through the Diophantine method. So this is not a proof that is really the dynamical degree, but at least the arithmetic degree that you calculate iterating over the rationals coincides with the largest root of this recursion relation. So probably it is the arithmetic degree. So the methods, as I said, of using the autonomizations to calculate the dynamical degree of a second order recursion relation rigorously was shown to be indeed rigorous for maps of the plane. For higher order maps, we have no idea, but it seems to work. Another example is quite a recent example by Claude Vialet, which is this simple looking map, which has one horrible length 28 singularity pattern. Again, it has singularity confinement and a dynamical degree, which is approximately this number. You can do probably the most simplistic non-autonomous extension. Just stick a function of n in front of the rational function, require that you have exactly the same singularity pattern. You get this condition on the function, which by the same trick that I explained, by whenever you see a zero, you put a plus here. When you put and the corresponding multiplicity, and when you see an infinity, you put a minus with the corresponding multiplicity.
And what about the dot?
The dots are just regular values that depend on the initial conditions. So the dots denote anything that is not 1, 0, or infinity. They're more complicated.
And they do not impact the...
No. So you can play the same game, so that there's actually a one-to-one correspondence between this condition and the pattern, as I explained in the two-dimensional case. And then the greatest root of the corresponding characteristic equation, which is written down here, is exactly that number. So again, probably this is really, and again, the Diophantine method gives the same approximation. So again, the method seems to work, at least in this case as well. Why? We have no idea why it works. We have no idea of how to go about a proof. All the techniques that we used for all the geometric techniques that we used in the two-dimensional case They simply don't exist. So we have no idea why this is true. This seems to be true. Now, why did I mention in the title that there might be a problem with the way we define integrability? There is no general classification theorem in the sense of de la Favre for higher order maps. So we don't know what the types of degree growth can be, and we do not know how the degree growth impacts the existence of integrals. So simply because it's something you can calculate. We say that if the degree growth is such that the algebraic entropy is 0, so the degree growth is sub-exponential, then we say that the map is integral. But we don't know whether such a map will have integrals. For maps of the plane, we knew that in those cases there would be integrals, or at least invariant vibrations, and that there was some physical notion of invariance or symmetries, and that you could explain why you want that map to be integrable. For higher order maps, we don't know. And actually, this is a recent example that I came up with Basil Grammaticos. It's a coupled system with three free parameters, z, beta, and gamma. And when all of them are free and non-zero, there's one rational invariant. But there's no singularity confinement, nothing. And the degree growth is actually cubic. So you think this might be integral. But there's only one invariant. And this is a fourth order system. If you want it to be algebraically integrable, just simply, then you would want 3 invariants. You could think there might be some Poisson structure, and then you might think 2 invariants would be sufficient to have integrability, but this only has 1. Of course, we haven't shown that there's only 1. We can only find one rational. When you impose this special condition between gamma and beta, then all of a sudden you have singularity confinement, and the degree growth drops. Now, that is not, as I tried to explain, singularity confinement is related to this notion of special cancellations happening in the iterates, so that the degree growth drops is not in itself special, but it drops to a quadratic degree growth. But still, there's only one rational invariant. Now, if you specify special values for beta and gamma, which of course satisfy this relation, then all of a sudden things become more interesting, because all of a sudden you have a second invariant, and there is a Poisson structure, and so this system is Liouville. And it's not only Liouville integrable, but you can actually integrate the thing. Basically, you can express the general solution in y, and in x in terms of the x's are just y-sums p functions, and the y-ends are infinite sums of p functions. You can actually physically integrate the system. And there's a continuum limit in this case to basically a Lamé equation. And actually, what I described here, this hierarchy of properties, is exactly the type of hierarchy of properties that you have for the Lamé system. So if I write Lamé like this, is just the definition of the second order defining equation for the P function. This is a Lamé equation. If you have 2 free coefficients, they're generic, then you have branching infinitely many times throughout the complex plane in the y-end. In the y function, I wrote yn, but it should be y, I'm sorry. If A is special, if it's basically a numerical coefficient of this type with m any integer, then the y's become meromorphic. That's known since Hermite. I think maybe it was Hermite who showed this, probably. Hermite has a very nice monograph on this. And then for special values of B, so basically the correct discrete spectrum, or the Lamé potential, then all of a sudden you have not only meromorphic function, but you actually have y's that are finite sums of p. So you have exactly for this discrete function, you have exactly the same type of hierarchy of, in a sense, analytic integrability, analytically nice properties of your solutions. Now the problem is there any way to characterize this type of hierarchy of integrability? I mean, the degree growth itself won't do it, because these 2 cases have the same degree growth. Is there some refined notion of integrability based on degree growth and singularity structure that would allow you to at least surmise that there will be extra invariance, or that there would be a Poisson structure, and that you would be close to something you would physically want to call an integral system? So that's the real challenge for higher order systems. But integrability becomes much more subtle, and we don't have any clear handles on how to measure that type of integrability. Now there's another case, which is this case, which is also sort of annoying. This case has been around, this equation has been appearing in lots of papers. I think, as far as I know, the earliest reference is a paper by Andy Horn and Ray Inoue, about 11 years ago, where they constructed Y systems for SOMAS 4 sequences. And they came up with this recursion relation, which has cubic growth, and two singularities. One has singularity confinement, and the other one is just you enter the singularity, you never get out. And they sort of explained why the cubic growth is there based on the properties of the SOMAS 4 sequence, which is nice. But this system is actually fully integrable by a very stupid trick in a sense. There's one invariant, one autonomous invariant, which is this thing. Now, if you look carefully, you see actually that this invariant can be integrated. So the system is integrable by integrating the invariant. This invariant actually can be integrated in this way. So this combination actually has this behavior in terms of the original invariant. And so this would be some kind of non-autonomous invariant, if you want. You have a new free function, Q0, and then the map itself is integrated by recognizing this as a discrete boundary equation. So this generalized Y system is actually integrable in terms of this QP1 equation, but it has only one autonomous invariant. So the real question, the real challenge is to find some clever, even a heuristic way would be nice to link this type of integrability to special singularity properties or to growth properties, probably a combination of both. But there are plenty of examples like this, where the maps, if you focus on autonomous invariants, then you will always be lucky. But the map is still completely integrable. And then the last example, if I have 1 more, 2 minutes? Yes?
5 minutes.
Okay. This is an example that comes from, not from maps, but from partial difference equations. So I'm now working on a 2-dimensional lattice, not just on Z, but on Z2. And how is it? The n direction is this, and this is the m direction. So m is vertical, n is horizontal. And there's this very famous equation, which is a lattice equation, which is a discrete version of the Liouville equation. I mean, it's not visible that it is, but there is a continuum limit to the Liouville equation, which is not too hard. When I say it's a discrete version of the Liouville equation is, in a sense, linearizable with some kind of holograph transformation. This equation has a similar property. So if you define initial conditions on this hook, so the black dots will be initial conditions, and the gray dots are the evolution of the initial conditions in the northeastern direction through this relation. Because the equation, as you see, it's defined on this fundamental quadrilateral, so everything in black propagates northeast if you want. And then you can actually integrate 2 ways. I've integrated now down to this line. So this is just a linear relation in terms of some fn functions that are defined by the initial conditions on the n-axis. But I could have done n and m are interchangeable. I could have integrated over there. So also in this sense, it is a nice discrete equivalent of the Liouville equation. It's explicitly linearized and hence solvable. If you calculate the degree growth, now in terms of all the initial conditions, so I have initial conditions here, all of them distinct, independent, in the m direction as well, so on this hook. And then I start calculating using this relation all the iterates, which will be all rational functions of, for example, the 5 here will be a degree 5 rational function of these 6 initial conditions. You see that degree growth is basically linear. That's by 1 here, by 1 here. On the diagonal, it jumps by 2. It's basically linear. Now, if you change the initial value problem in this slightly pathological way, where now the initial conditions are given on 2 staircases that form some kind of wedge in this quadrant, this is still well defined. There are no contradictions. It's a well-posed evolution. And then when you try to calculate the degree growth, you see that on the diagonal, it's a very strange degree growth. This is a numerical result for 200-300 iterates. And it's the kind of growth that we've never seen before. It's a weird thing. Now, you would want to say that this is non-integrable. It is non-integrable in the sense that it doesn't linearize anymore. There's no way to linearize the equation on this type of initial boundary value problem. So in that sense, I would say it's no longer integrable. Of course, the lesson is not so deep. We're not dealing with a map. We're dealing with basically the discrete equivalent of a partial differential equation. So what you would call an integrable system does depend on what kind of initial value problem or Gauss problem you're discussing. But this is a very striking example because the behavior is completely different. You had nice linear growth, and then simply by changing the initial value problem, you get incredibly strange growth properties. So that's the last thing I wanted to say. If you want to try to extend everything that I introduced today, notions of degree growth, and try to link that to notions of integrability for maps, and try to extend that to partial difference equations, then there's an enormous amount of work that needs to be done, because basically we don't know anything about any possible relation. Okay, that's where I start. Thank you. Yes.
So there's a classification by Adler, Bobenko, and Suris
Yes.
of lattice equations that are integrable. I guess the discrete Liouville equation falls in that classification. It's in terms of multidimensional consistency.
It's multidimensional consistency, and what they call integrable is the fact that it's multidimensionally consistent. Yes. But it's only consistent for the boundary conditions that I showed you.
So consistency is just around the cube usually.
Yes, but if you want to use that notion to, for example, construct a Lax pair, then and basically build maybe some transfer matrix based on the Lax pair, and that only works for these rectangular hook-like initial value problems. So whether consistency itself is a good notion, a good definition of integrability, to be honest, I don't know. I mean, I want to integrate the map afterwards.
And if you change your wedge, instead of having an acute angle like this, you have one more than pi/2. Do you still have this problem of having this?
It gets even worse.
Oh, worse.
Yes, it gets worse. I didn't show you. I can show you some slides. If you increase the amount of information coming from the past, then the growth even increases. You can bend one edge to the beyond the vertical, as you said. That means that you increase the number of initial conditions that impact a certain iterate in the future, and it gets even worse. It gets faster.
So the best case is pi/2?
That's the best case. These type of initial value problems, we don't know what is going on. Thank you very much.